Hi, my name is Tej, and I'm going to be talking today about a paper we wrote a year back. It was also my master's thesis last year. I wrote it alongside my advisor, Dr. Dhirisha Kuritipuri, and unfortunately, we couldn't present it last year, but I was really excited to hear that it was continued this year. So let's get right into it. The paper we wrote is called Relational Neurogenesis for Lifelong Learning Agents, where we talk about the process of relational neurogenesis, where we talk about the relationship between neurons and how we can use the mechanism of neurogenesis to accelerate and increase the performance of lifelong learning agents. So let's get right into it because there are a lot of things we have to cover. So a quick thing, a lot of you are familiar with the concept of lifelong learning, but I thought I'd just cover it once so you understand the paradigm from which this paper is written. The lifelong learning is basically the ability of an agent to learn subsequent tasks one after another. So you go from, say, task 1, task 2, task 3, task 4. And then it's very important for the lifelong learning agent to be able to remember these tasks, not especially in the order that they were learned, but what happens is, most of the time, is using traditional machine learning and deep learning algorithms, we encounter several challenges with this process when you try to learn independent different tasks one after another. So one of the main problems is the inability to learn tasks that you've learned previously because they are partially overwritten by the new tasks that you're trying to learn. And that process is called catastrophic forgetting. Additionally, when you learn more tasks, it eats into your network capacity, and that is something you have to keep in mind when you have to train lifelong learning agents for a continual set of tasks. Then we have to talk about the unsupervised learning mechanisms, where you do not always have a supervisor telling the AI algorithm, "Hey, we have transitioned from task 1 to task 2 to task 3," and in the absence of such a supervisor, can we still learn? And then obviously there are the questions about learning costs and learning rate. That means how fast can this agent actually learn these tasks? And also by learning costs here, I mean, how many times does an agent have to go through a scenario to learn it? And that may translate to real world costs or hardware costs or simulation costs. There are a lot of costs involved. So one of the things we're going to talk about is neuroevolution, and this is different from it's different from evolutionary algorithms in the fact that in neuroevolution, we're actually changing the architecture of the network that we're running. And actually, this was brought up by the previous talk as well, so I was really glad to hear that. So in this paper, we're going to talk about four processes: neurogenesis, which is the addition of nodes; synaptogenesis, which is the addition of connections to those newly added nodes, or in case of a sparse network, connections between existing nodes; neuronal death or termination, which is the removal of nodes, as well as synapse termination, which is the removal of edges, because it's necessary to balance out these mechanisms so that the network doesn't just explode in size. So here's some of the very key questions that I'm going to be addressing. How can neuroevolution assist lifelong learning? Because we've seen different approaches towards tackling this problem, and it's very interesting to see how changing the capacity of a network would be able to help incorporate more information. More than that, it's also important to identify how can the agent learn without a supervisor providing context about task change. And also, what mechanisms can we identify that can help preserve information? So the paper that we wrote actually targets this by suggesting new mechanisms for neurogenesis and synaptogenesis, as well as a mechanism for preserving information through activity tracking. We also developed a few environments because we thought that the environments that exist don't exactly target lifelong learning as such. So we developed some new environments to specifically target the problem of catastrophic forgetting within lifelong learning environments. And we also made kind of a communication network, a communication library to communicate between our simulation environments and our code. So let's talk about the context, which I'm going to be talking about in this paper with respect to reinforcement learning. So let's take an example. In this example, the agent, or basically the agent through which our algorithm is acting, is, for example, a spider who is going to transverse an environment which could be a maze. And it gets different positive and negative rewards in this environment to model its behavior. A negative reward could be fire, where if it gets too close to the fire or it touches the fire, it could get burned, so it gets a negative reward. If it gets food, it gets a positive reward, so it encourages that behavior. And it learns to navigate the mesh and also trade off these rewards. In a lifelong learning scenario, we would have the same setup, but we would have different tasks trained one after another. So in the first task, the agent would have to look for food. In the second task, he would have to stay away from fire. In the third task, he would have to fight off a foe or a predator or run away from one. And in the fourth task, you would have it basically seeing if it can work with another spider, if it's like a friend. This is an example of 4 different tasks, and we trained them one after another. So this is what such an environment would kind of look like. It would have a spider different types of senses, which would be our inputs, as well as olfactory, visual, and sensory types of senses. And from the reinforcement learning paradigm, our base algorithm is a very simple deep reinforcement learning network, which collects the inputs, and based on that, performs a forward pass through the deep learning network, has output activations, which are used to update weights, and then we collect network parameters. And that's very important that we collect these network parameters, because I'm going to talk about that in a second, about exactly where our framework kicks in. So let's talk about the relational neurogenesis architecture and how it actually helps in this problem. So for example, this is an example of a deep reinforcement learning network, which is the feed-forward network as such. And as a forward pass is conducted, we actually track the activations and we store them in a matrix. And this is important because we will address this in a bit. But we track these activations at every time step so that we can identify which nodes were which nodes had key importance towards the previous time step or towards the previous set of actions. So this is the framework that we've actually proposed. We initially start by collecting a different set of parameters. We collect the scores, we collect the weights, the activations, the outputs, the rewards, and we use them to calculate a secondary intermediate set of metrics, which is, for example, the weight change, the average global activation, the score gradients, the relative activation from one node to another. And I will cover exactly how these are important. But basically, we use these intermediate metrics and then compare them to thresholds that we've identified for particular tasks. And then we can decide whether or not a network based on the parameters is suitable for adding or removing nodes. We can identify the need for neurogenesis or synaptogenesis or termination of either. And we will talk about the different mechanisms. We have about 8 mechanisms. But I won't be able to cover all of them, so I'll just cover the first 3, which is with respect to neurogenesis and deciding when neurogenesis needs to take place within a network. So let's talk about the mechanisms themselves. Let's talk about the first mechanism, which is Plateauing Merit. This mechanism actually helps identify it helps identify 2 things. One thing is it helps identify when a task changes from one task to another. We notice that if you're having a self-evaluatory mechanism within the agent where it's evaluating its own performance, like a health bar or anything, then it's able to track it's able to create a performance score of its own performance within the environment. And as soon as it notices that it's not able to keep up with the environment, we can actually track that as a gradient change or an average gradient change over a number of episodes. And then we can use that to make the agent self-aware of task change, because when it changes, we notice a very large dip in performance. Similarly, we can also use the metric of plateauing merit, which is the gradient of change of its own self-evaluated performance, and we can compare that against the threshold. In addition to task change, if there was no task change, it also identifies that the agent is unable to learn new information due to an inherent insufficient capacity within the network. So if the merit score starts plateauing, then you can actually use this as a metric to identify that the network needs to add new nodes so as to increase the capacity to add in additional information. A secondary mechanism is learning opposite concepts. And this is one of the biggest problems that we have. When we're trying to learn, for example, in a T maze, which is a common reinforcement learning problem, where an agent has to decide whether to go left or right and rewards for both. Then what happens is in some of the episodes, you notice the agent goes left, some of them goes right. So what happens is if you identify the key weight that's being, or the key weights that are being targeted during this learning paradigm, you'll notice that the weights tend to oscillate. So if you track the weight, the absolute weight, and the change in the weight magnitude, you'll notice that for the weights that are actually being pulled in opposite directions, there will be a divergence of these two parameters. Whereas if the weights are continuing to not be pulled, basically they're not being affected too much, or there's task overlap, then you'll notice that the weights stay similar. So by viewing this and by seeing the change, the large oscillation in weights, you can identify that a particular weight is being pulled in opposite directions, and then you can provide or add a neuron to provide relief towards this particular. You can provide relief for this particular weight change, and it'll help alleviate this problem if you connect that new neuron to the set of previously connected weights. The third mechanism is also a low margin of confidence. So what you notice is from your output layer, you can compare the output activation at every time step to every other output activation. And then you can identify which, if a neuron shows a very, very low similarity between outputs, then it shows that it's unable to differentiate between two particular classes or two particular states. And so you can add additional neurons to provide the increased separability. And this is another important reason for performing neurogenesis, because that acts as a relief mechanism to the network, which would otherwise go into a catastrophic forgetting scenario. And all these mechanisms are compared to thresholds, which we actually sweep using, for example, a genetic algorithm. This is one of the poor parts of this algorithm, is that we have to identify these specific thresholds to find out where these individual mechanisms can perform best. Because if the thresholds are not set properly, it could cause network expansion or network compression really badly. Okay, so let's talk about exactly where we're evaluating these algorithms that I said. So we created a set of virtual environments, which I introduced previously with respect to the spider. So this was the first set of environments. And when I say set, there are four environments within an environment, four tasks rather, four sub-environments within an environment. So when we train the spider, you see that it actually is able to learn. After some time, it learns to stay to navigate the maze as well as interact with fire. But we try to trick the spider by actually making the fire dual purpose. For example, we wanted to add some inherent non-linearity to the system. So when the spider gets a negative reward for touching the fire, but if he goes too far away from the fire, he gets cold. So we wanted to see whether the dynamic network can capture these nonlinear relationships between the environment and the agent. Then we had multiple different tasks within the environment, which we trained on sequentially. For example, we trained the spider to forage for food. We trained it to run away from a predator, which I didn't have a snake, so I had to put in an additional spider. And we also made it interact with multiple variants of itself, where we had two agents learning, and we wanted to see whether they would fight or they would benefit each other. And depending on the situation, we observed both behaviors. We observed coexistence and we observed competition. And we also observed that it didn't really know what to do with each other because they hadn't seen other spiders before. Then we thought, hey, we should probably make a much more complicated environment to test for real world problems, because that was kind of a toy problem. So we kind of made a second set of environments, and this was before the Australian wildfires, so it became quite relevant after the paper was published. But it was targeting the set of fires that we had in California. Sorry. So we have a drone that is exploring a forest environment, and there are multiple tasks. The first task is navigating the forest. Second task would be locating trapped civilians. Third part is rescuing those civilians to a safe point. And the fifth task is, if I put in multiple agents, how do they behave? Do they really help, or do they start behaving erratically? And we train on these tasks sequentially, and we notice that the agent, after training on 4 tasks, is able to recollect information, and it is able to successfully locate and trap. So this was an experiment to see if the same algorithm is able to scale up for larger problems and larger data sets or more complex environments. And we noticed that was it could. So let's talk about exactly what the results were. Because when we evaluated these, it's very important to see task to task how much information is being forgotten. So overall, it's a good algorithm. It was noticed that the reinforcement, the relational neurogenesis algorithm in black here, it has a really good sample efficiency, and it's able to run really, really quickly as compared to some of the state-of-the-art algorithms out there. And this is in single task performance. This is not from continual learning standpoint. This is just the single task performance. We just wanted to investigate that for a second. So it converges, or it really learns really quickly because it has a lot of overhead mechanisms for incorporating information at every time step. It's able to somewhat match state-of-the-art performance, not quite, but almost. But we noticed that there are very, very heavy computational overheads that actually, if you run them for the same time on the same set of resources, you notice that it probably takes, for example, 500 episodes to reach the same. It would take 500. It would complete 500 episodes in the same time a competing algorithm would finish 800. So we also noticed that this is an example of what the neurogenesis looks like within the network itself. If you look at continual learning performance, where we compare it to independent performance, we notice that the relational neurogenesis in the right has the least amount of task degradation if you train on the sequence 1, 2, 3, and 4. And obviously, we did shift this around the sequence of training of the sequence of environments. And this is for just the sequence itself. But more interesting than the ability to mitigate catastrophic forgetting is when we notice the network size, because we initialize it very sparsely and we then count the number of nodes as the network grows on multiple tasks, we notice that it kind of converges towards a very nice sweet spot, which is under the number required for larger algorithms like EWC. Which obviously do not have the dynamic architecture, but our maximal size after all 4 environments was still smaller than some of the static algorithms. And it's very important to notice network size in dynamic architectures, because you can keep adding nodes and your network size would grow exponentially. And that's undesirable because we're trying to go for lifelong learning. So the network size should probably taper off after some point, depending on the amount of shared information between tasks. And another interesting analysis we did was to see the initial versus the final sparsity. So if you compare the initial network that we generate is a sparse network, not a fully connected network. So depending on the amount of initial sparsity, whether it was 0 to 100%, the network is able to introduce nodes and introduce connections to make up for any level of sparsity. And the best thing we noticed was it's able to converge to the same solution space, basically irrespective of where it started off, initial sparsity, it's able to converge to a final point, which it identifies as the most optimum point for evaluating the network or evaluating that particular environment. Obviously, there are different points for different environments, but we notice that sparsity does not affect it, or the initialization sparsity does not affect it, because the network's neurogenesis and synaptogenesis, and as well as the terminations, kind of balance out and stabilize at particular points. So what's next? Basically, we noticed that relational neurogenesis is a very good set as a combination of evolutionary neuroevolutionary algorithms as well as TRL, and it can learn continually with minimal effect of catastrophic forgetting for a set number of tasks. It minimizes and kind of optimizes the network growth, which is the best part. And the best part is it doesn't require a supervisor for task switching, because it's self-aware when tasks get switched. But we noticed that RN is very computationally expensive. Future work is we need to kind of unify and optimize these mechanisms, because they're very diverse and there are too many things to track. And the last thing is we have different environments that we can talk about in the future. So we can explore different, more diverse set of environments. We can introduce more photorealism because we noticed that the forest fire it didn't go over well with the undergraduate students. So they were like, we need more realism. So we've been developing more realistic environments, as well as procedural generation to create infinite variation so that we don't have to hand model these environments every time. And also there's transfer learning where we can train on these simulated tasks, because a lot of these tasks like forest fires don't really have corollaries where we can train in real life. We can't really create a fire to train in real life. So you'll have to train these agents in such simulated environments and then transfer into real world scenarios. Thank you. Thank you so much.